what exactly is security? You probably have heard this term before, but you might not know exactly what it entails. And specifically today we're going to be talking about security in the context of web applications. So this entails authentication, injection, cross-site scripting, and HTTP versus HTTPS. So today mainly we'll be talking about authentication, but if we have extra time at the end, we'll talk about injection, cross-site scripting, and HTTP versus HTTPS. Okay, so here we have three people trying to connect to a web server. And up to now, we haven't really dealt with authentication in any form. So up to now, we've set up routes on our web server, and we've made it so that different clients can connect to this web server and perform different sorts of actions. But we haven't done any verification of who the clients are. And this is important when we're dealing with things such as bank accounts or something, where people need to be able to be identified properly. So we need to be able to tell different people apart. And to do this, we need authentication. And, okay, so let's try and figure out how we can do this. Okay, so we're going to think about this in the context of a bank. So, disregard the whole computer thing for now and pretend that we just want to go to a bank. Okay, so say this is me, and this is the bank. Okay, so if the bank wants to tell me and other people apart, how can we do this? Does anyone have any suggestions? How do you think banks tell different people apart? Yeah, ID. So, okay, great. So they know our names. When we walk in, they know our names. So say I want to go to a bank to sign up for a bank account. The first thing I give the bank is my name and some sort of identification or code. Okay, so now every different person who signs up at this bank will give the same thing to the bank, the name and their identification. Okay, so this seems to work for now, right? So say I wanted to pay someone $100. What could I do? So I could go to the bank, take out a piece of paper, write my name and some identification, and then hand this piece of paper to the bank, right? So I would have something like this. And yeah, so I could write this down on a piece of paper for every different transaction I want to make and give it to the bank. So if I wanted to pay Aaron $100, I would write my name, my ID, and I want to pay Aaron $100. And then I would just give this paper to the bank clerk. And if I wanted to pay someone else $50, I could just make another piece of paper like this and give it to the bank. Okay, so this seems to work, right? So are we done? Do you think this is satisfactory, or what do you think? Well, it turns out that this is actually extremely bad. We don't want to do this at all. Never. So, okay. So now, why exactly don't we want to do this? So there arises a problem with this strategy. Every time I want to pay someone $100, I give a piece of paper, then another piece of paper, then another piece of paper, multiple times throughout the session of a day. But what's the problem with this? I mean, it seems fine, right? I mean, I'm just giving them to the bank clerk. Well, the problem arises when we lose one of these pieces of paper. Say while you want to pay 300 people on one day, and you're giving the bank clerk 300 pieces of paper. Imagine that it's a very unlucky day for me, and a gust of wind blows in through the window and blows one of these pieces of paper out. And then Hunter, who's over here, is now very happy because he got this piece of paper with my name and my identifier, right? So now that Hunter knows my name and my ID, the bank has no way of telling apart Hunter and me, right? Does that make sense? So clearly it's unoptimal to include both our name and identifier in every single piece of paper we give to the bank. And these pieces of paper are analogous to requests that you're sending to your web server, and the bank is analogous to a web server. Okay, so how can we foil Hunter and keep our name and identification safe? So the bank decides to get a bit smarter and implement some sort of system where the bank can minimize the amount of times that we send the bank our information. So now the bank instead of, say I go to the bank once, the bank wants it so that I only need to tell the bank my name and my identification once, and then every subsequent time, the bank will know that every paper after that passed from me is me. And, okay, this might sound like complicated at first, but there exists this strategy to do this. Okay, so let's go back to the first piece of paper that I give the bank on a visit to the bank. So the first thing I'm going to tell the bank now is just a piece of paper with my name and my identification. Okay, so I tell the bank my name and my identification, and the bank internally, the bank has a table of like name and like ID. So when I go to the bank, I tell the bank my name and my ID. So the bank looks up in their own table my name and my ID. And since the ID I gave matches the name I gave, the bank says, okay, this is Aashish. So I'm sure this is him, and I'm going to give him some sort of token that he can use in the future. So this is like the second case with sessions. So after I give the bank a piece of paper with my name and my ID, what can the bank do? So the bank sends back a piece of paper with a randomly generated string that is like huge. So think of like a 20-character string that's completely random and unreadable. So like think the type of string you'll see in that image, except that they'll be much longer. So we'll get this like HJ83B or like some random thing like that, very long. Okay. So now I have this random string that the bank just gave me. And there's no way anyone could guess this string unless it's impossible because it's so long and it's made of random letters. If I asked you to give me like a random string of 120, you wouldn't say HJ83B, or it's like very unlikely. So, okay, now I have this string that the bank has given me. So now, for every subsequent interaction I have with the bank, I can, instead of including my name and my ID, I can just tell the bank this string that it gave me. Okay, so now say I want to pay Aaron $100. What I'd say is something like this. I'd say a session token, which is HJ83B, and I tell the bank the amount. So the difference between this and the previous case was that before we were sending our username and our password with every single request to the bank. Whereas here, all we're telling the bank is, well, initially we're telling them our username and our password, but then the bank gives us a random string. And for every subsequent request in this bank visit, I'm going to give the bank just the session token that the bank gave me. Does that make sense? Yep.
So in the first example, you said this identifier blew away in the wind and somebody intercepted it.
Yeah.
What prevents that same thing happening?
Yeah, so over here, up to now, like, this isn't actually prevented. But the difference is here, for every single request we were giving the bank, we were including our name and identification. Whereas over here, only the first piece of paper we're giving the bank has our name and our identification or password. Every other piece of paper doesn't have our name and our password and just has like this random string. So we've already reduced the problem a lot. And okay, so say it's the end of the day and I'm about to leave the bank. So I'll tell the bank I'm done, like I'm done for the day, I'm leaving. Then the bank says, okay, like you're good to go. And when the bank says that, what they're going to do is they're going to say that, okay, this session token is now invalid. So, okay, so just to like repeat that, when I first go to the bank, I give the bank my name and my identification. The bank says, okay, I will make a table of a user to session. And so I go to the bank, I give them my name and my ID, they check to make sure that it's me, and then they add me to this table. They put my name and then a random string of long length. And then for every request I send the bank from now on, I just include that session, and the bank can look and find the user with that session. But at the end of the day, when I leave the bank, I tell the bank I'm leaving. And then what the bank does is that they remove my name from the session. So now the difference between this and the previous case is, okay, say I go to the bank and I want to pay 300 people. Say a gust of wind blows in on the 200th paper. And then that paper flies out of the window, and then Hunter gets his hands on that piece of paper and thinks, I'm going to steal some money next week. The difference now is that because so Hunter has managed to steal my session token, but at the end of the day, when I'm about to leave the bank, I'll tell the bank I'm leaving, and then the bank invalidates my username and my session token. So then when Hunter goes to the bank next week and tries to present the bank my session token and the operation to pay him $100, the bank says, you can't because that session was used 1 week ago. I know that it's invalidated. Does that make sense? Okay. So, are we done? Yep.
What if Hunter intercepts your name and password when you're trying to start a session?
Yeah, so that's a problem. So, we'll get to that later, but the point just between these two examples is that you only have one vulnerable request at this point. Okay. So, yeah, we're clearly not done. So, yeah. And just to bring this back into the context of like computers and how this affects you. So all these pieces of paper we're giving the bank are in the form of different HTTP requests that you're sending the web server. And but when you're actually making your requests from your browser, you don't actually need to fill out your username and password every time because of the existence of something called a cookie. And basically what this means is that the website will tell your browser that, okay, set your client's session cookie to this random string of numbers. And then from then on, your browser will always send that session token for every request it sends to the server. So in other words, before we were using, we were manually like inputting different parameters into like get requests or post requests. But for cookies, these were included automatically for individual sites. So a site can tell your browser to set a cookie, and then for every request your browser sends to that site, it'll also send those cookies. So it's just, think of it as a more convenient way of sending things. So like before we had to include our session token in every request we made to the server. So think of it like, now our paper implicitly has our session like embedded into it. So think of it like this. Imagine that these papers could be identified just by like the type of paper alone. You don't actually need to write your session token every time. Yeah. Okay, so there still is a fundamental problem with this approach we had, and this will bring us into password storage. Okay, so before I drew this table of name to ID, or think of it as name to password, right? So this is how the bank actually verifies who I am, right? I go to the bank, I tell them my name, I tell them my password, and the bank says, okay, you're good to go. Does anyone think there's any problem with this? Any ideas? Okay, so, I mean, it doesn't seem like there's a problem at first because only the bank has access to this name and password. But let's think of this in the wider scheme of things. Imagine that this wasn't just one bank, but this was like 100 banks as part of like a chain across the country or something. Now, again, say that Hunter is really desperate to get my money, right? He really wants my money. So he wants it so badly that he's going to sneak into the bank at night and steal this table. He's just going to steal it. Okay? So this presents us a problem. Because if Hunter manages to steal our username to password table, then he can go to any bank around the country that's part of the same chain and give them my name and my password, and all the other banks will think it's me because he's managed to take our name and ID. So this is like analogous to getting this is basically, yeah, this is analogous to getting your database leaked. So imagine that you were hosting a site, a bank site or something, and someone somehow managed to get your database of names and passwords. From now on, your users are completely dead, right? Because all of their info is gone. So, is there any way we can make this better? So, there actually exists some math that can help us with this. Okay, well, first let's try a naive approach. We don't want to store people's exact names and identification in our table, right? Because then if someone steals it, then they're completely free to go and do whatever they want with your identification. So let's say that the bank tried some primitive encryption on your passwords. So, okay. So on the original thing you give the bank, you give them your name, your ID, and your ID. This is like for the initial thing to tell the bank that you are who you are. So what the bank clerk can do is, instead of just writing down your name and your identification, what the bank clerk can do is write, okay, I'll write down his name, but instead of putting his raw ID, I'm going to like change his ID a bit so that it'll be like unrecognizable. So, for example, in this case, all the bank clerk does is he shifts all the letters by 4. So like instead of writing ABC, he would write like DEF or something in his table. So now like all of the passwords will be unrecognizable. And so okay, well now if our password isn't exactly what we told the bank initially, then how can the bank know it's us if they've already like mashed up our password? So, okay, what the bank can do is they can just reverse the password, reverse the encrypted password, and cross-check it with the password we told the bank. So, okay, so originally I would say my password is ABC. Okay? And then the bank stores it inside their internal table. They store it as DEF. Okay? Okay, so now, say I go to the bank again, and I tell the bank that my name is Aashish and my password is ABC. What the bank will do is they'll look up my name in the table they have and see that my password, the encrypted password is DEF. And then they can reverse this by just shifting the letters back over 4, and they'll see that ABC matches DEF shifted 4. And how does this help us? This doesn't help us that much, but all it means is that whenever Okay? So this actually helps us a lot because now, instead of just storing DEF in the database, what the bank will do is they're going to store, they're going to run, so what the bank clerk does is when I initially give them my username and a password, what the bank clerk will do is, okay, in his table he's going to write my name, and he's going to SHA-256 hash my password. So in this case my password was Linux. So the bank clerk will say, okay, I'm going to calculate the SHA-256 digest of Linux. And he gets the output, and then he stores that output in his table. Okay, so how does this help us? So this helps us because now, if Hunter manages to steal our table, or that table, what can he do with this? Like, okay, sure, he has my hash password, but like, what can he do with this? He can't actually reverse this into my original password. So if he goes to any other bank and tells them, I know his hash password, the bank will be like, that's like really sketchy. You shouldn't really know people's hash passwords. But you clearly still don't know the plain text password, so I'm not letting you get your money. So, okay, this seems to solve our problem, right? Does this make sense to people? Okay, great. So, are we done? Turns out we're not done at all, unfortunately. Okay, so let's go back to this example. So we already established that SHA-256 is one way, and there's no way to reverse it, right? Okay, but let's just try something out real quick. Okay, so let's just go to the site and take this hash, put it in there, press decode. I don't know if that. Let me try a different site. I don't see it.
It's at the top left. It says
Oh, it's
legit.
at the top left. Okay, yeah. So, yeah, like, how did this reverse our password? I mean, like, I promise you that it's impossible to reverse a SHA-256 hash. So how could this just give us our password? Okay, so let's get back into this, the bank analogy. So Hunter has managed to steal the table of names to hashes, okay? And it doesn't, like, he can't actually reverse these hashes. But it turns out that there is a way that he can retrieve my password. What he does is, he has this friend, this very suspicious friend, who has a ton of compute power at his disposal, okay? Or maybe not even compute power, but his friend is like, has a habit of stealing from banks. So his friend has already previously constructed a table of like random words to their hashes, okay? So, okay, we've already established that we can't reverse the hash back into the word. But okay, so what his friend has done to avoid this problem is he has just, imagine like every word you know, like say apple, banana, or like whatever, like, or bread, or like all of the words you can think of. He has taken all of those words and calculated the hash of all of those. Okay? So he's taken all of these words and like all of these combinations of words, all of these like short passwords, and just calculated the hash of all of these. Okay? So this takes like a lot of memory. It'll be like gigabytes and gigabytes of data. But he has managed to construct a table of random words to hashes. Okay? So now that Hunter goes to this sketchy friend of his and asks him, yo, can you help me out? I want to sneak into this bank and like steal someone's money. And so his friend is like, sure, I have this convenient table that you can use. So, okay, so all Hunter has to do now is take this table that his friend has already made and take my hash on the right-hand side and compare it against every word he has in here, or every combination of words he has here. Yep.
There's something I don't understand, is that if, I don't know how the function SHA-256 works, but if I could tweak it, like offset by just one click all the hashes and then this could void the table or it could make it obsolete.
So, that's what we'll get into for now. But, so the reason, so this table, like, can reverse the passwords, but the problem is that if someone has an existing table, this won't work because someone can just reverse it. Okay. Yeah, so as was just mentioned, you definitely aren't done with this because someone can just like reverse these hashes if they've computed these ahead of time. I don't know why it's okay. So this is what we can do. This is one thing we can do to fix this. There exists something called a salt that you can add to the end of your passwords. So, okay. Now the bank decides to get smarter, right? So instead of just storing a table of my name to my hashed ID, the clerk will do something a bit different this time. When the clerk gets when I first give the clerk my name and my ID, what the clerk is going to do is, for every single ID I give to the clerk, he's going to say, okay, I'm not going to hash his ID. What I'm going to do is I'm going to hash his ID plus some arbitrary string that we're going to call the salt. Okay? So, instead of hashing, in this example, instead of hashing Linux, we're going to hash Linux and then a random string at the end. Or Windows and then a random string at the end. Or Mac and then a random string at the end. Right? So, how does this help us? So this helps us because Hunter can no longer use his existing lookup table because it's very unlikely that his sketchy friend has constructed a lookup table for adding for this specific salt at the end of it. Because every different bank company in the world will be using a different salt. It's very unlikely they'll all be using the same salt. So that means Hunter needs to construct his he needs to consult his sketchy friend and ask him to create this lookup table specifically for this bank and specifically for this salt. Does that make sense? Okay. So, are we done? What do people think? I mean, this seems pretty good, right? I mean, now every single different banking company in the world has a different table, so it should all be good. But unfortunately, this is not good still. I mean, it's still better. We're miles better than we were at the start, but this is still not good. Okay. The problem with our previous approach was, okay, sure, we've added this extra piece of information to the end of all of our different IDs. But, okay, so say that Hunter really, really, really wants to get my money. So what he does is he consults his friend and asks him, okay, construct this lookup table using this salt at the bank, for the bank. Okay, and right now we're assuming that Hunter manages to find out our salt because he has blackmailed one of the bank clerks and like forced the bank clerk to tell him what the salt is. So Hunter knows the salt, and he can just construct a new lookup table based on this salt to generate a reversing scheme. And okay, so once he generates this table himself, and he manages to crack my password, but not only has he managed to crack my password, but he can use this same lookup table on everyone else who uses this bank. Like, once he constructs this new table, he can get my password, he can get Aaron's password, and he can get David's password. All at once. All he needs to do is construct one table. And this one table will take, like, a long time to create, but he can still do it. Okay, so how can we do better? So what we can do to make this better is to, instead of having the same salt for each person, we can change it up a bit. So, okay, so the bank clerk before was just hashing our IDs plus the salt at the end, right? Okay. So the bank clerk can make this better by, instead of just adding the same salt to the end of every person's password, he can instead change the salt per different person who goes to the bank. So instead, say that salt was like a function of my name or something, or like some random thing. So salt is now a function of name, and or like any other thing that's unique to each user. So now instead of having a table of name to just ID, to hashed ID, what we're going to do is we're going to add a new column called salt. And so what the bank clerk is going to do is, for each different person, he's going to compute a salt based on his name. So I might have one salt, and Aaron will have a different salt, and etc., etc. So what does this do for us? All this does is it changes the salt for each different person. But this is actually helpful because now if Hunter manages to construct a lookup table, so Hunter can obviously find out the function that we're using to salt, the function that we're using to generate the salt per person. Or he can just find out what salt each different person is using. So, I mean, he can still find my password if given enough time, a lot of time. What he can do is he can just, in his lookup table, he can create his lookup table based on my salt, and then hopefully find my name, given by just reverse checking the hash in his new lookup table. But the difference is now, because everyone's salt is different, what happens is that, okay, he constructs a table for me, he manages to steal all my money, but he can no longer take Aaron's money or David's money, because Aaron and David don't have the same salt at the end of their IDs, right? So Hunter would now need to construct a different lookup table for every different salt in the database. Does that make sense? So in other words, before our salt wasn't a variable. It was just some additional constant thing we added to the end of our strings to make sure it couldn't be used with existing tables. But making the salts variable completely changes things, because now we don't have a constant thing appended to the end of everyone's password. What we have appended to everyone's password is now a function of their name. It's not a constant anymore. If that makes sense. Okay, so we're finally done for now. This is pretty good, and like it's very unlikely that Hunter will be able to steal my password from just by stealing the database. Are you lost? That's completely fine because this might not be it might not be that intuitive. But luckily for us, we don't have to actually deal with all of this ourselves unless we really want to. And there exists something called something called Passport.js that we can use to solve these problems. Because what Passport.js does is it just abstracts all of this away under the hood, so we don't need to worry about any of this. But it's important to know how this works. You probably noticed this in action because when you go to sites and say you forget your password, if you click this forgot your password link, you probably noticed that when they send you the reset email, they never actually include your password in the email because they don't actually have your password. All they have is a hash of your password. That's why so that's why they don't send you your password back when you click forgot your password. What you have to do is you have to generate a new password. So this is kind of cool because the bank can verify that it's you based on your password, but they don't actually have your password. Okay. So there's one last thing we have to go over that's a lot simpler, but can anyone guess what these are? Yeah. These are the top 25 most common passwords. Okay? And okay, yeah, so these probably these probably aren't very you look at these and you're like, yeah, I could definitely have guessed those. And this is why it's very, very, very important to have a strong password. Because for this reason, we spent all of this effort trying to figure out a good scheme where we could just say our ID and salt our names. We could say our ID, add a salt to it, the bank will hash it, and oh, we're all good, right? We've done all this stuff to it. But now, imagine your password was 1, 2, 3, 4, 5, 6, right? Okay, now what Hunter's going to do is he's not even going to bother building a lookup table. What he's going to do is he's going to go to different banks and just guess random passwords. He's going to guess password, and for a million people, and it's likely that at least a couple of people will have this password. And this is why sites emphasize so strongly that you need a strong password. If you don't have a strong password, all of this protection is useless because people can just guess the most common passwords and steal them. So sites aren't just trying to be annoying when they say make sure your password has a number or it's not just words or something. This is why they do that. Yeah. Okay, so we have 8 minutes left, and we have a couple topics left, so I'll let you guys choose what you want to go over. If anyone wants to go over any of these, just shout it out, because we can't go over all of them. So we have injection, cross-site scripting, and HTTP versus HTTPS. Does anyone have a preference? Cross-site scripting? Okay. Okay, so what exactly is cross-site scripting? You might have seen it being referred to as XSS. And this is because X is a cross. But so basically what cross-site scripting means is you manage to inject something into a web page so that it will do something different. So just as a quick example before we go into how exactly we can implement this, you see here we have a learning modules page, right? And you guys might have used learning modules before. You might have had some of your classes on it. But if you go to this link, you'll notice that there's now a cat embedded in it. And the thing is, beforehand, this cat did not actually exist if you go to this page. I'll explain what exactly this cat means. But if you just go to this page, You see that it says membership service failed.